Hey everyone. We're looking at station 10, and f of x is the cube root of x, or x to the 1/3. I'll be using x to the 1/3 for this, I imagine, because I don't want to take the derivative of that. I'd much prefer to take the derivative of that, but we're only looking on negative 1 to 1. One of the things that I've been saying to you for a while is, think about what you're doing here graphically. And I haven't even read the question yet, and already I'm thinking, well, it's that cube root of x graph, stopping at 1, starting at negative 1. And that's our graph. I do see that vertical slope there at x equals 0 that I told you about last year. And so maybe that'll be important in this problem. Let's see. Part A, show that f of x on this interval does not satisfy the hypothesis for the mean value theorem. Okay, well, let's think about the preconditions. What were the preconditions for MVT? Well, the first precondition was that f is continuous on negative 1 to 1. Is that true? Well, sure. This function exists at all those points. There's no place where this function doesn't exist from negative 1 to 1. But what about the second precondition? Remember? F is differentiable. That means the derivative exists on open interval negative 1 to 1. Aha! No, that's not true, is it? We just got through saying that this is a vertical slope here, an undefined slope. So I don't have a derivative at x equals 0. And now we caught that because we were thinking graphically. If I'm not thinking graphically, well, let's think about calculus. F prime of x is going to be 1/3 x to the subtract 1, or subtract 3/3, so I got minus 2/3 here, which is 1 over 3 cube root of x squared. Now, here's my derivative of f. Notice, if x equals 0, then I have 1 over 0. I have undefined. So, since f prime of 0 is undefined, the preconditions for MVT are not met. And if you don't think that's enough, you could say f is not differentiable. Everywhere on negative 1 to 1. But I think that should be sufficient. Okay, good. Nice. So we've got that. Part B, graph f of x. Oh, well, we know what that graph looks like. We just saw that graph. Oops, we're stopping. And we want to connect. It says, with the line connecting 1, 1, and negative 1, negative 1. So this is the graph that they wanted, and this is that line connecting the endpoints. Okay. Find any value c on that interval from negative 1 to 1 that satisfies MVT. So even though we didn't meet the preconditions for guaranteeing a place where f prime of c would be equal to f of b minus f of a over b minus a, even though we're not guaranteed that, we're going to see if we could still maybe find a place like that, because check it out. See this line? See how slopey and positive slopey it is with its slope of 1? Well, my function seems to take on a slope of 1 at these two other points. So I think even though that we haven't been guaranteed that x equals c exists by the mean value theorem, we can in fact go through the mean value theorem and find these places that will exist. So let's take a look. And for us, we still don't know where c is, but we can say that we're looking for f of 1 minus f of negative 1 over 1 minus negative 1. Well, f of 1 is 1 minus f of negative 1 is negative 1 over 1 minus a minus 1. So that's going to be 2 over 2, or x equals 1. Now, it's around about this point that students start inventing all kinds of math. Like, I think I'm supposed to do this. Rather than, let's look at this. What does this notation say? It says the derivative of f equals 1. So you know what you got to do now? You got to take f prime and set that puppy equal to 1. All right, well, we found f prime before, remember? F prime was 1/3 x to the minus 2/3. So we want to know when this derivative equals 1. Okay, so how do we solve that? Well, I'm going to multiply both sides by 3. X to the minus 2/3. And I multiply here by 3 and here by 3. And those will cancel, and I'll have a 3 there. Yeah? And now, so I think what I'm going to do here is write this as 1 over x to the 2/3 equals 3. In fact, I don't want to deal with that, so I'm going to multiply both sides by x to the 2/3. And so now I've got, in fact, let's bring the 3 back over. X to the 2/3. So I don't want x to the 2/3, I just want plain old x. So I'm going to raise both sides to the 3/2 power. Now, here's something important that I tried to impress upon you in pre-cal last year. See that? That's you taking the square root of both sides of the equation. And because you're taking the square root of both sides of the equation, you know what you need to remember? Plus or minus. Hey, guess what? Here's the positive one. There's the negative one. So when x equals plus and minus 1/3 to the 3/2, MVT, no, I don't want to say that. I want to say when x equals this, the slope on f is equal to the slope of the secant from -1 to 1. Okay. Fabulous. So please keep in mind the mean value theorem. You need to know the mean value theorem and its two preconditions. And after you've shown those two preconditions, using the mean value theorem is I've got a slope, and I set that slope equal to my derivative, and then I can solve for that specific c, where the slope of the secant, the slope between those 2 points, the average rate of change, is equal to the instantaneous rate of change, the slope at a point. Okay, what's station 11 say? Station 11, ooh, it's algebra-rific. Station 11 says f equals x square root 4 minus x, and I think we're going to want that. We're asked when is this function increasing, decreasing, and find any extrema. Don't forget to justify them. Okay, so we need a derivative here. I've been seeing recently that some people are forgetting that the product rule exists. So please make sure when you take this derivative that you actually use the product rule. So we're going to have 1 times 4 minus x to the 1/2. That's the derivative of this times that, plus this times the derivative of that. Well, I'm going to bring down the 1/2. 4 minus x. Don't forget the minus 1/2 up here. And don't forget to take the derivative of the inside. So then let's do some GCF factoring. We're going to take out 4 minus x to the smaller power. And what's left over? Well, we factored a minus 1/2 here. So that's going to leave us with 4 minus x. Now we have our plus sign. And we've got negative 1/2 x. So I guess I want this to be negative 1/2 x. When I tidy this up, I get 4 minus 3/2 x. And I get 4 minus x to the minus 1/2. And there's my f prime. Now remember, we've been talking about setting factors equal to 0. When I set this factor equal to 0, because this is in the denominator of f prime, I'm going to be finding when f prime is undefined. So x equals 4, f prime undefined. What about setting this one equal to 0? 4 minus 3/2 x equals 0. 4 equals 3/2 x. X equals 8/3. Okay? Now, it might be useful for us, now that we've got those two values, to also think about this function. And I don't know if you've noticed, but in the last few years, people have been awfully concerned about you knowing domain. And so, what's the domain of that? That's right. It's not 4 to infinity. It's negative infinity to 4. And 8/3. And let's call that f prime for now. The function doesn't exist over here. So if I plug a 5 in here, 4 minus 5 is negative 1. I'm not taking the square root of negative 1 for this problem. So that doesn't exist. So 4 is actually an endpoint. Remember, maxes and mins can occur not only when the derivative is 0, but also when the derivative is undefined, i.e. at 4, or at the endpoints on a bounded interval. And so, yeah, I definitely want to be thinking about 4. So this is my f prime sign chart. Conveniently, I threw f prime away. It was 3x minus 8, because that'll get me 8/3, over square root of 4 minus x, I believe. So, yeah, because that, when I set that equal to 0, I get this. It's probably slightly different than that, but let's just go with this, please. If I plug a 0 in here, I get positive over positive. And if I put something between 8/3 and 4, well, between 8/3 and 4 is something called 9/3, or 3. And then I'm going to get, whoa! Yeah, that didn't work. So I guess I have to go back to algebra land for a moment. Hold on. F prime, again, is going to be 1, 4 minus x to the 1/2 plus x times 1/2, 4 minus x to the negative 1/2 times the derivative of the inside. And so we took out 4 minus x to the smaller power, and we were left with minus 1/2. We were left with 4 minus x minus 1/2 x. And so we said, oh yeah, that's going to be 4 minus 3/2 x. And so we set this equal to 0. In fact, let's just go from there, because we certainly had our two critical points. I feel good about 8/3. 8/3 and 4, and nothing exists here. So if I put in a 0, this goes away, that goes away. I've got 4 over square root of 4, that's a positive number. And I'm looking for something here like 3. So that's going to be 9/2. 3 times 3 is 9/2. 9/2 is 4.5. So 4 minus 4.5 is a negative on top and a positive on the bottom. Negative divided by positive is a negative. So I do have the sign change that I need. I can determine that there's a max at x equals 8/3. But what about over here? Well, remember, this is an endpoint, and f is decreasing until it gets there. F is decreasing until it gets there. Well, if my function is decreasing until I get to 4, that means that I have a minimum here. Okay? So, and what else can we say? We were asked for when is the function increasing, and so from negative infinity to 8/3. When is the function decreasing from 8/3 to 4, and maxes and mins. So let's see if we can do the writing that we need to do here. F is increasing on negative infinity to 8/3 because f prime is greater than 0 on negative infinity to 8 thirds. And f is decreasing on 8 thirds to 4 because f prime is less than 0 on 8 thirds to 4. Okay. And finally, we can say there's an x at x equals 8 thirds because to the left of x equals 8 thirds, f prime is greater than 0, and to the right of x equals 8 thirds, f prime is less than 0. Don't forget the endpoint. We have a min at x equals 4 because x equals 4 is the right endpoint, and f prime is was negative. F prime is less than 0 to the left of x equals 4. Okie doke. All right, there was station 11, and our last station, station 12, says, oh, it's the same function. How convenient. Except now we're asked about concave up, concave down, and inflection points. Okay, so for station 12, let's see if I remember that derivative this time. Not 8, but 4 minus 3/2 x. And then we also had 4 minus x to the minus 1/2. There's f prime. I know it's possible to get the information I want from f prime, but I have a really hard time knowing when this is increasing without finding f double prime. So I'm going to find f double prime, and again, that's product, so I need to use the product rule. This times the derivative of that plus this times the derivative of this. So I'm going to bring down that negative 1/2, and I'm going to leave the inside alone. I'm going to subtract 1 from that, so now we have minus 3/2. And don't forget to take the derivative of the inside, which would be negative 1. So what can we take out? Well, I'd like to take out the smallest power. So f double prime is going to be 4 minus x to the negative 3/2. What else can we take out? Well, we've got, that's negative times negative, that's positive. I can definitely take out a half from each of these, though I'm tempted to take out a negative 1/2. Let's do that. And so now I'm left with this 3, and I factored a minus 3/2 out, so I still have a 4 minus x here. I took out the negative, so I still have that, minus, and this is all gone, but I still have that, 4 minus 3/2 x. Okay, so this is going to be 12 minus 3x minus 4 plus 3/2 x. Combine like terms, 8 minus 6/2 plus 3/2 is minus 3/2. That doesn't feel right. Oh, yes, it does. Okay, so we've got that. We've got this negative 1/2, which is just a vertical compressing factor. It doesn't change the critical numbers. The derivative is still undefined at 4, but now I've got this f double prime equal to 0 happening at 16 thirds. So I've got 4, I've got 16, whoa, 16 thirds. 16 thirds. That's bigger than 4. That's over here. But here's the issue with 16 thirds. The function doesn't exist over here, right? We're still dealing with a square root of 4 minus x. There's nothing over here. So even though we'd like it algebraically to be 16 thirds, yeah, no. I don't have any critical points on f double prime. So if I pick any number like 0, where'd my x go? There's my x. If I plug a 0 in for x and a 0 in for x, I end up with positive times negative is a negative over a positive, which is negative. And so this is telling me that my function is concave down everywhere. Concave down everywhere. Well, that's interesting. Let's take a look. Here, we were talking about x square root 4 minus x. And I just want to see what that graph looks like. Zoom 6 should be sufficient. That is. Look, it's concave down everywhere. That's so cool. That's what I found here. F double prime was always negative, and therefore F is always concave down. And that's what we're asked to find in part A. F is concave down on negative infinity to 4. Don't say negative infinity to infinity because this doesn't exist past 4. B, F is never concave up. In fact, you might want to say why. What's your justification for this? And what we'll say is because F double prime is less than 0 on negative infinity to 4. There we go. And inflection points? No. C, there is no sign change in F double prime, so there are no inflection points. All right, well, there we go on F. So those were the review stations. I hope they help. I hope you're able to make use of them. Let me know if you have any more questions. Okay.